Good morning, everyone. Today, we would like to discuss about molecular orbital theory. So, in this theory, actually, we are dealing with the formation of molecular orbitals, the stability of molecules, and the electronic configuration of electrons in molecules. So, first one, let's discuss about the postulates of molecular orbital theory. First one, the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in various atomic orbitals. So we know that in atoms, electrons are present in atomic orbitals. Similarly, in molecules, they are in molecular orbitals. Second one, the atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. So symmetry and energy matters while an atomic orbitals combines to form molecular orbitals. Then third point, while an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more. So that's the third point. Then fourth one, the number of molecular orbitals formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are also formed, and one is known as bonding molecular orbital while the other is called anti-bonding molecular orbital. So generally the bonding molecular orbital is represented without a star and anti-bonding molecular orbitals will be represented with adding a star. Then fifth point, the bonding molecular orbital has lower energy and hence greater stability than the corresponding anti-bonding molecular orbital. So while comparing the stability of these two bonding as well as anti-bonding molecular orbital, the bonding molecular orbitals possess better stability and lower energy when compared to anti-bonding molecular orbitals. Then look at the sixth point. Just as the electron probability distribution around a nucleus in an atom is given by atomic orbital. So definition of atomic orbital is actually the region around a nucleus where there is very high probability to meet an electron. Similarly, the molecular orbitals actually gives the probability distribution of electrons in molecules. Look at the seventh point. The molecular orbitals, like atomic orbitals, are filled in accordance with the Hofbauer principle, Pauli's exclusion principle, Hund's rule, etc. So, filling of electrons in molecular orbitals also follows Pauli's exclusion principle, Hund's rule, and Hofbauer principle. Now, we have certain assumptions. We have implemented certain assumptions to solve problems in molecular orbital theory. The first assumption was linear combination of atomic orbitals. In this particular assumption, what we are doing is we will assume so many forces are negligible in the case of when atoms combines to form molecules. And this is such a assumption. So let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms A and B. Each hydrogen atom in the ground state has one electron in oneness orbital. The atomic orbital of these atoms may be represented by the wave function psi A and psi B. Mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and a subtraction of wave function of individual atomic orbitals. So, a molecular orbital arises by adding and subtracting the wave function corresponds to atomic orbital. So, here it adds, and in the case of anti-bonding molecular orbital, it subtracts. The molecular orbital sigma formed by the addition of atomic orbitals is called bonding molecular orbital, while the molecular orbital sigma star formed by the subtraction of atomic orbital is called a anti-bonding molecular orbital. And this is the energy diagram of bonding as well as anti-bonding molecular orbital. From the diagram, we can see that the energy of anti-bonding molecular orbital is much greater than that of bonding molecular orbital. Then molecular orbitals electronic configuration. So electrons are filling in molecular orbitals based on certain rules. We know that it follows Hofbauer principle, Pauli's exclusion principle, and Hund's rule, etc. So based on that, scientists has developed a certain order based on their energy, symmetry, etc. So for diatomic molecules containing up to 14 electrons, that follows the order sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than pi 2px equal to pi 2py less than sigma 2pz less than sigma star pi star 2px equal to pi star 2py less than sigma star 2pz. And this is how the filling of molecular orbitals takes place for diatomic molecules having a total number of electron which is less than or up to 40. And for diatomic molecules containing number of electrons greater than 40, it follows the order sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz. Look at this, the sigma 2pz comes first before pi 2px and pi 2py, then pi star 2px, pi star 2py, then sigma star 2pz. Then stability of molecule. See, the MOT actually describes the stability of molecules. If Nb is the number of electrons occupying in bonding molecular orbital and Na the number of electrons occupied in anti-bonding molecular orbitals, then if the molecule is stable if Nb is greater than Na. So greater the number of electrons in bonding molecular orbitals and increases the stability of the molecule. Similarly, if there is a very good amount of very large amount of electrons in anti-bonding molecular orbital, then the molecule will be unstable. Then more bonding orbitals are occupied and so the bonding influence is stronger and stable molecule results. The antibonding influence is stronger and therefore the molecule is unstable. So keep in mind one thing, when number of bonding electron increases, the stability of the molecule will be increased. Keep in mind the stability related to the number of electrons in bonding molecular orbital. Then bond order. Bond order is actually a parameter. So bond order is defined as one half of the difference between number of electrons present in the bonding and the anti-bonding orbitals. So we have the equation bond order is equal to half of Nb minus Na. As bond order increases, bond length decreases and bond strength increases. Hence, stability increases. Keep in mind this is very important. Also the equation you have to you should know how to find the bond order of a molecule. Then molecular orbital electronic configuration of molecules. First one, hydrogen. Its configuration is 1s2 since they contain a total of 2 electrons. Then the bond order is 1, which means between two hydrogen atoms you can find a single bond. Then in the case of carbon molecule, the electronic configuration of the molecule is given sigma 1s2, sigma star 1s2, sigma 2s2, sigma, pi 2px2, pi 2py2. The carbon molecule contain a total of 12 electrons. 12 electrons and all of them occupy in this manner. Okay. So its bond order is 2, which means between two carbon atoms, there will be a double bond. Similarly, we have already found uh, the molecular electronic configuration of boron molecule, nitrogen molecule, oxygen molecule, etc. And it is here. Then carbon monoxide molecule. So look at this. In carbon monoxide molecule, it is actually a heteronuclear diatomic molecule. The one nucleus is of carbon and the other one is of oxygen. The ground state molecular orbital electronic configuration for carbon monoxide is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz2. So in carbon dioxide, they contain a total of 14 electrons. Sorry, in carbon monoxide, they contain a total of 14 electrons and they are distributed in this manner. Then calculating the bond order and its application, we already discussed. Now we are moving to the last comparison of VBT and MOT. So first of all, let's discuss the similarities. Both are based on quantum mechanical principle. Both postulate the formation of bond on account of overlapping of the concerned atomic orbital. As per both combination of atomic orbitals yield bond orbitals, the combining orbitals should have comparable energy and symmetry. So these things are explained by both VB theory as well as MO theory. Both uses approximation methods, namely LCAO approximation and Born-Oppenheimer approximation. Then points of difference. That's the thing. VBT partially focus on the role of valence electrons of atoms in the bonding process so that atoms do not lose their identity during bonding, while MOT considers molecule as a whole and during the combination the identity of atomic orbital changes entirely. Then VBT concentrates on localized bonding while MOT concentrates on delocalized bonding. According to VBT, in majority cases, bonding results by the overlap of half-filled atomic orbitals, while according to MOT, the overlapping of atomic orbitals may be half-filled or completely filled, provided they have comparable energy and symmetry. So in VBT, for overlapping, it requires an atomic orbital containing half-filled electrons. But in the case of MOT, it doesn't say so. Instead, whatever be the filling, whether it is fulfilled, half-filled, or if there is no electron, then if it has sufficient energy and symmetry, those can combine to form a molecular orbital. So it is stated by MOT. Then VBT provides easy visualization of how electrons are shared in a covalent bond. The MOT model is more complex, particularly for larger molecules. VBT provide a good description of the directional characteristics of the covalent bonding, which is helpful in explaining geometries and properties like stereoisomerism. MOT finds limited application on this respect. So VBT gives geometrical aspects. We know that it actually explains the geometry of why certain molecules exhibit certain particular geometry. Those things are explained by VBT. So the stereochemistry is mainly explained by VB theory, of course. And those applications are limited in the case of MOT. The last point, VBT makes incurrent prediction about electronic structure and the properties of oxygen. VBT predict that O2 is diamagnetic while MOT successfully explained the paramagnetism of O2 molecules. So that's all. Thank you.